What's up, people? Intro to derivatives, the chain rule. The most powerful derivative rule you will ever find is the chain rule. The chain rule is seriously one of the most powerful differentiation rules. If you're wondering to yourself, what the heck is differentiation? Remember, differentiation is simply the process of taking a function and finding its derivative. So differentiation is the process of finding a derivative. And again, the chain rule is one of the most powerful rules in that process. This rule deals with composite functions and adds a surprising versatility to the rules that we've actually already learned. It can be used in many situations, but primarily with composite functions. So before we actually talk about the chain rule, we should probably talk about what a composite function is. So a composite function is when a function can be viewed as a function within a function. So here are some examples. So here we have a traditional, regular, old school, normal polynomial function, x squared plus 5. But imagine if we took that function and put it into the square root function. So in this scenario, y equals the square root of x is like the parent function, and we're composing that function with x squared plus 5. So we're taking this x squared plus 5 and we're plugging it into the parent function, the square root of x. This is called composing. We're literally taking a function, the square root of x, and we're composing it with another function, x squared plus 5, and we get the resulting composite function. Here's another example, sine of x, pretty traditional standard function. But imagine that we take 6x and put it into that function. So once again, in this scenario, our parent function would be sine of x. And what we're doing is we're putting 6x into that function. So we're taking sine of x, but instead of sine of x, we're composing it as sine of 6x. Pretty simple. Here's another one, 6x minus 7, pretty standard generic polynomial linear function. But imagine we take that function and put it into another function, x to the 5th. So in this scenario, our parent function is x to the 4th. What am I talking about? X to the 5th. And imagine that we put 6x minus 7 into that function. Again, composing. We've talked about this a while ago. And here's another one. This is actually, not trying to trick you here, but trying to make sure we take our time with this. So we have x plus cosine of x. That would be like our parent function. And then we're plugging 4x squared into the cosine. So the x is actually just kind of standing alone on its own. So that's just kind of its own little thing. And then we're adding cosine. But we're composing cosine with 4x squared. So this part in the back would be a composite function because it's cosine composed of 4x squared. Here's one more example. We have sine of x, pretty traditional standard trig function. But imagine that we put that into sine squared. Now hold on, you might be like, what? What's going on? In this scenario, the parent function is x squared. Because remember, we touched back this in our trig unit, sine squared is really sine of x all squared. The x is not squared, it's the entire sine that gets squared. So again, we have a parent function of x squared, and we're taking sine and plugging it into that. So again, these are just a couple examples of composite functions where a function goes into another function. And I'll even be honest with you, like, you know, seriously, if you think about a traditional standard polynomial function, 2x to the 5th, right? That's a pretty standard polynomial function, right? You could look at this in a way as a composite function, right? All we're doing is we're plugging in x. I mean, all functions in a way are composite functions. They're composed of x. So this function is an x plugged into it, hence 2x squared. So again, if you look at a function, right, if you look at a parent function as simply something being done to a value, right? So, you know, if I look at the square root is this, right? That's the square root of something, right? That's what a square root function does. It's the square root of something. And even if I plug x into that something, hey, I just composed the square root with an x. But again, I'm getting more advanced here. I'm taking the square root of something and I'm plugging in something a little bit more complicated like x squared plus 5. So even at the end of the day, just to be honest with you, all functions in a way are composite functions because all functions are composed of x and so forth. So hopefully that makes sense. And if it doesn't, it definitely will develop that skill as we go throughout this video here. All right, so one way of thinking of a composite function is this. F of x is a function. And let's let g of x be another function. So we could literally take g of x and plug it into f of x. So g of x would be a composite function, literally putting g into f of x. Again, you should have done this in Algebra 2, and we even talked about it a couple months ago in pre-calc as well. Excuse me. Here's another way of thinking of a composite function. Again, let f of x be a function, pretty standard function, f of x. And let's try to make this even more simplistic. Let's let u be another function. And we could literally take u and plug it into f. So f of u would literally be a composite function putting u into f of x. And I know right now it says f of u, and I know what that looks like. And you're like, why would you choose f of u? That kind of looks bad. Sorry. Almost any calc book you look at, that's how they do it. So I'm sorry. I know it doesn't sound great. I laughed when I was in high school too. All right, anyway. So to utilize the chain rule, I'm about to teach you. I'm going to teach you the chain rule here very shortly. You need to first be able to identify what the function u is. Like, what is the function that is inside of the function, right? So it's helpful to be able to, when you see a composite function, you should be able to recognize the parent function and the function that's going into that. So let's actually practice that real quick here. So for these 4 examples, I want us to write down what's the parent function and then what's u that goes into that function. So in this first case, the parent function would be like 2 over x. And then we're letting u be 3x plus 1. So we're literally taking this function u and plugging it in for x. And that's what creates the function 2 over 3x plus 1. So 2 over x is a pretty generic standard function. It's not too complicated. But when we take another function, 3x plus 1, and plug it in there, it does become a little bit more complicated. In this next example here, the parent function would be x cubed, something cubed. And we would let u equal x plus 2 because we literally took u and plugged it in for x, creating x plus 2 to the third. In this next example, let me grab a different color here. This next example, the parent function would be sine of x. Again, a very generic trig function. And u would be 2x. We're literally taking u and plugging it in for x. And then in this last example here, again, you'd say, well, wait a minute, that's not a composite function. Well, again, even a very easy polynomial function can be viewed as a composite function. So in this case, the parent function would be 5 times x cubed, and then u would just be x. And I know it seems silly because you're like, yeah, duh. But I mean, that's the point that I was trying to make earlier, that all functions can be viewed as composite functions if your u, your other function, is just x, because you're plugging x in, and that which creates 5x cubed, right? So remember, functions are like machines, right? So to try to make sure you understand this, like, let's look at this example right here, right? The parent function is the machine. The parent function says, give me something and I'll cube it. Give me something and I'll cube it. Give me something and I'll cube it. So we could say, all right, I'll give you u. Let's let u be x. Okay, so we get x cubed. Or I could say, well, let's let u be x plus 2. All right, now we got x plus 2 cubed. So again, look at the functions as, don't even look at them with an x. Look at it as something, right? So this first one right here is 2 divided by something. And if we make that x, well, then it's 2 divided by x. If we make that 3x plus 1, then it's 2 divided by 3x plus 1. So again, it's the idea of a parent function is just, hey, here's what you need to do to something. And then the u is the something that we plug in for that. And again, some kids see this really quickly, and others it takes a little bit of time. But if you need to be able to understand this to be able to understand the chain rule. All right, so here is the official chain rule. If we have a function y equals f composed of u, and if that function is differentiable, which just means that it's possible to find the derivative, and then we have this second function u, which u is another function. For example, we could call it g of x. We could define u to be another function, g of x. And that function also needs to be differentiable, which means you can find the derivative. And what then we do is we say, okay, well, like composite functions, we could plug g into f, right? This should make sense, right? Again, if I'm letting u be g of x and f is composed of u, well then if u is g of x, then I'm plugging g of x in for u and I get f of g of x. Okay, that's composite functions. I hope by now you know that. So here is how you find the derivative of a composite function. You take the derivative of the parent function times the derivative of u. Another way of looking at this, an equivalent way of looking at this, is saying, hey, remember this d dx, let's just say, oh, this should be an x right here, by the way. All right, so d dx, saying, find the derivative of a composite function. Remember, a composite function is a function plugged into another function. To find the derivative of a composite function, you take the derivative of f, that's the parent function, and you multiply it by the derivative of g of x, which you're plugging in. Now, I know a lot of you are probably thinking right now, what? Like, I get that last slide was probably very confusing. In fact, I was confused too. I remember learning this when I was in high school. I was like, what are you trying to teach me? Give it a chance. But I have to go over all this because if you look up the chain rule in any textbook, this is what you're going to see. But I'm going to do my best to explain it to you as simply as I can. So just bear with me. Listen to me. Here's how you use the chain rule. First, examine your function and determine the parent function and the u. The u is the function within the function. This is what we were practicing a couple slides ago. Take the time to figure that out. Then you're going to rewrite the function as f of u. And you might be like, well, how do I do that? I'm going to show you. It's really simple. You literally are just saying, hey, let's plug u into the function. Then, here's the rule. Find the derivative by taking the derivative of f of u and multiplying it by the derivative of u. So this is what you probably won't find in a lot of textbooks, but this is how I think it makes the most sense to think about the derivative with the chain rule. So to find the derivative of a composite function, you basically find the derivative of the parent function. And then you multiply that by the derivative of the function within it. Now, it still may seem confusing, but that's because we haven't seen an example yet. Once we see some examples, you're going to realize how unbelievably easy this is. All right, here we go. Here's our first function. All right, so the first thing I'm going to do, step one, has nothing to do with derivatives. I'm simply going to break this down. The parent function is the square root of x, and I'm plugging in x squared plus 5. So x squared plus 5 is the u that is going into the parent function of the square root of x. Okay, fantastic, awesome. Step two is to write f as f of u. So I'm literally going to write this function as the square root of u. And you're saying, well, what do you, well, hold on, look, this is so, I'm just trying to make this super simple. U is x squared plus 5. So I'm just taking that out for a second, and I'm replacing it with u, because I'm letting u equal x squared plus 5, right? So the square root of u would be equal to my original function. So the statement I have here in green is technically equivalent to the original problem as long as you understand u equals x squared plus 5. All right, now here's how you find the derivative. This is easy. To find the derivative, first, you find the derivative of this, the parent function. Now, to find that derivative, I am going to briefly write that as u to the 1/2, so I could use the power rule. So hopefully everybody knows how to do that, right? Square root is the same as a 1/2 power. So now I'm going to find the derivative of that. The 1/2 falls down in front. My new power is 1/2 minus 1, which is negative 1/2. Remember, that's the power rule. 1/2 falls down in front. The new power is your old power minus 1. So 1/2 minus 1 is negative 1/2. And then you multiply that by the derivative of u. And the derivative of u is simply 2x. Again, power rule. 2 falls down in front. 2 times x to the first is just 2x. 5 is a constant. The derivative of 5 is 0. So there's my answer, but now I just have to clean it up. What I'm going to do now is I'm first going to replace u with what u equals, right? I want the derivative with respect to x. I don't want a u in there. So remember, u is x squared plus 5. So I'm just going to put an x squared plus 5 in there for u. Raise to the negative 1/2 times 2x. Now I got to do some algebra to clean up my answer. This is the officially answer. That is the derivative, but I got to clean it up. So first off, a 1/2 times a 2, that's going to reduce to a 1. 1/2 times 2 is 1. Now, I don't like negative exponents, so I'm going to leave this x in the numerator, and then I'm going to move the x squared plus 5 to the denominator where it could have a 1/2 power. And I'm okay with that as your answer, or you could take it a step further, and anytime you see a 1/2 power that is equivalent to a square root, so we have the square root of x squared plus 5. There is the derivative. So let me walk you through that one more time. I first split up my parent function from my u. Then I rewrote the parent function as just, well, the square root of u. Then the actual chain rule says this: find the derivative of your function, your parent function. That was easy. 1/2 fell down, u the negative 1/2. Multiply that by the derivative of u, which was very simple as well, 2x. Then I did have to go back and replace u with what it was and clean it up. That's the chain rule. Not that bad, right? All right, let's do another example here. This one's actually really easy. All right, so once again, the first thing I have to develop is what is my parent function? My parent function is x to the 5th, and u is what is inside of that, 6x minus 7. The second step is literally rewriting f, or my original function, as u to the 5th. And again, how simple is that, right? It's 6x minus 7 to the 5th. I'm basically like reverse substitution, right? I'm just letting u equal 6x minus 7, and I'm replacing the 6x minus 7 with a u. All right, now I'm ready to find the derivative. I mean, it's really pretty simple. I think by the end of this, you're going to like it. All right, so to find the derivative y prime, the first thing is you got to find the derivative of your function. That's 5u to the 4th. Yeah, that was pretty easy. And then you multiply that by the derivative of u. The derivative of u is just 6, right? The derivative of 6x, 1 falls down, 6 times 1 is 6, x to the 0, x to the 0 is just 1, 6 times 1 is 6, 7 is a constant, derivative of 7, 0, gone. And then again, now I'm gonna do a couple little cleanup things. I have to replace u, because u is 6x minus 7 raised to the 4th times 6. And of course, I can finish this off by doing 5 times that 6 and get a 30, 6x minus 7 to the 4th. And I would never, ever ask you to actually do 6x minus 7 to the 4th. That would just get way too much algebra. Just leave it as that, 6x minus 7 to the 4th. So now maybe you're breathing a little bit easier. Yeah, chain rules seem kind of confusing in the beginning, but boy, this is starting to seem kind of simple. Let's do another one. All right, step 1, identifying the parent function. The main overall function is sine of something. And u is what goes into that. That's the 6x cubed. So the second step is just realizing that we could just simply rewrite that as sine of u. That's a single parent function, sine of u, but we're just kind of holding off or kind of reverse substituting, right? The 6x cup, we're taking it away from the sine. All right, now that's it. Now we're ready to go. The third step, find the derivative. Y prime, it's the derivative of your function. The derivative of sine is cosine of u. I mean, it doesn't get much easier than that. Times, again, I'll even encourage a lot of parentheses here, times the derivative of u. The derivative of u is 18x squared. Hopefully everybody's getting really good at the power rule. 3 falls down in front. 3 times 6 is 18. New power is 3 minus 1, 2. There you go. There's the derivative. And again, good news is there's really not a whole lot you can do to clean this up. So I would just put the 18x squared in front. And then I do have to replace the u with what u is, 6x cubed. So there's your derivative, 18x squared times cosine of 6x cubed. All right, let's do another one here. All right, now this one's a little bit tricky, but again, the parent function is actually something squared. In the something, u is the sine of x. So I'm literally plugging sine of x into the function, which creates sine squared. Again, please remember that when the square is after the n, that's actually sine all squared, like that. All right, so that means that the original function is really just u squared. The parent function is u squared, and we're plugging sine into that. All right, so now we're ready to find the derivative. Y prime is the derivative of your function, 2u to the 1st, times the derivative of u. The derivative of sine is cosine. And we're almost done. All we have to do is replace u. U is sine of x, so we get 2 sine of x to the 1st, but I don't really have to write a 1 there, doesn't matter, times cosine of x. Boom, there's my derivative. I'm done. So easy. Now, once you get a hang, once you get good at using the chain rule, you can actually start using it quickly without all the steps. So I wouldn't recommend doing this unless you fully are like, yeah, this is easy. I'm getting this. This is simple. If you're feeling that way, you can actually begin to use the chain rule without all the hoopla and following the steps. Let me show you some examples here. So once again, if I want to quickly find the derivative of this, the first off is I'm recognizing that this is a composite function. But again, listen, it's not like there's a lot of steps, right? How easy was I doing those problems? But, if you're looking for an even little shorter way, here's how you do it, right? I just want to make sure I explain this. To find the derivative, again, I'm treating this as like one value. Right? I know it's more than one value, but it really is one value. Right? How many times have I said, hey, 3x squared minus 4, it looks like multiple things, but it's just one number. So again, all I can do is follow the power rule. 4 comes down in front, the 4 hits that 2, and you get 8. Leave the inside alone. You're not changing that, and you're going to raise it to the third. So that literally was using the power rule. 4 falls down in front. 4 times 2 is 8. There's my inside, which usually I would call u, but I'm trying to do this a little bit faster. And then 4 minus 1 is 3. But then here is where you got to remember, multiplied by the derivative of the inside. That's the u, right? And again, if you need to write u equals 3x squared minus 4 to help you understand this is great, right? But I'm trying to get you to understand that if you're really good at the rule, you could kind of bypass that. So 4 falls down in front, 8, 3x squared minus 4 to the third, but then you have to multiply by the derivative of the inside, which is 6x. How'd I get that so fast? Well, I'm looking at the derivative of u. 2 falls down in front, 3 times 2 is 6, 6x to the first. Negative 4 is a constant. The derivative of a constant is 0, so it's just 6x. And that's it, guys. That's it. So obviously I could clean this up. 8 times the 6x is 48x times 3x squared minus 4 raised to the third. So you're almost like you're leaving the inside alone and using the power rule. But then you have to remember, I have to multiply by the derivative of that inside. All right, let's do another one here that's a little bit more complicated, but just as easy. All right, so once again, listen, the power rule works with negatives, fractions, whole numbers, anything. So again, I'm just going to use the power rule. The 1/5 falls down in front, just like the power rule says, and I get 4/5. Leave the inside alone. My new power is 1/5 minus 1, which is 5/5. That's going to be negative 4/5. But then you have to multiply by the derivative of the inside composite function, the inside part. And that derivative is going to be 6x minus 6. Once again, 2 falls down. 2 times 3 is 6. X to the first. 1 falls down. Negative 6 times 1 is negative 6. My new power is 0. X is 0 is 1, so don't even write it. All right, and then that's it. That's my derivative. But of course, y prime. Of course, I want to clean this up a little bit. I don't like negative exponents, so all of this needs to move to the denominator. That way, it can have a positive exponent. So I have 4 times 6x minus 6. The 4 didn't want to go anywhere. The 6x minus 6 didn't want to go anywhere. And the denominator, I have 3x squared minus 6x to the positive 4/5. And then again, that 5 is down there as well. Don't forget that 5 was in the denominator. So there's my 4/5, 6x minus 6, but I did move the 3x squared minus 6x down, so it has a positive exponent. And I would not mind that as a final answer. Obviously, you could distribute the 4 to get 24x minus 24. I don't care if you do that or don't do that. Times 5, and then again, 3x squared minus 6x raised to the 4/5. How easy is that, guys? But listen, if you need to say, hey, this is my u. If you need to do that, go ahead. I encourage it. Go ahead. And then you're going to say, all right, so I bet essentially my function f of u is 4 times u to the 1/5. And then again, all you have to remember is the rule says find the derivative. That's where the 1/5 comes down. My new power is negative 4/5 times the derivative of u, which is the inside section. So by doing it without all those rules, all I'm trying to do is speed the process up. Don't hate me for it, sorry. But all I'm saying is say, listen, just leave the inside alone, right? We're going to have to replace it anyway. Like when I was following the rules, if I followed the actual rules, I have to replace u with 3x squared minus 6x anyway. So why as well just leave it there because it needs to be there anyway. I hope that makes sense to you guys. All right, and here's one more. So once again, the first thing I'm going to do is I don't like square roots at all. When you're working with derivatives, square roots are much better as a 1/2 power. So once again, I'm just going to go right ahead. Again, if you need to look at this as your u, that's the inside, that's fine. But I'm going to go right to finding the power rule. The 1/2 falls down in front times the cosine of x. Inside stays the same. My new power is negative 1/2. 1/2 minus 1. But then you just have to remember to multiply by the derivative of the inside, which is negative sine of x. So the chain rule has a lot to do with the power rule, but it's not just the power rule. All right, so all I got to do now is clean this up. Let's see here. The negative sign of x could stay on top, but I'm going to go ahead and move the cosine to the bottom as cosine x to the 1/2 because I don't like negative exponents. And then again, I would be okay with that, but one more step is making that the square root of cosine of x because a 1/2 power is the same as a square root. So there's your derivative. How simple is that? How simple is that? All right. Now, like I said in the very beginning, the chain rule is very versatile, right? The chain rule can be used, not sued, typo there. I'm going to fix it real quick before it annoys me. The chain rule can be used in so many places, even when the power rule, product rule, and quotient rule could have been used. So like we now have options. We now have several different ways that you can find a derivative. But at the end of the day, if you're asked to find the derivative of a problem, I don't care how you do it. Well, I have a lot of typos. I don't care what rule. Boy, oh boy, this is embarrassing. I don't care what rule you use. Just find the derivative. So here's an example of what I'm talking about. Here is a very basic function. And after the very basic rules, everybody should be able to say, oh, 15x squared, derivative, done. But listen, if you want to use the chain rule, you actually could. You could say, okay, I'm going to let u equal x. Therefore, my function is 5u cubed. Right? Again, all I'm doing is taking out the x, reverse substitution. And then I'd say, okay, the chain rule says, find the derivative of your function, 15u cubed, multiply it by the derivative of u. The derivative of x is just 1. 1 falls down in front. X to the 0 is, anything to the 0 is 1, so 1, right? Okay. And then we'd say, okay, well, let me clean that up. 15u cubed times 1 is 15u cubed. But then, if you do it that way, you have to remember to replace the u with what it is. Well, u equals x, so I'm going to replace it with 15x cubed. And I cannot believe I let this happen. It's a square. I'm so sorry. Even teachers make mistakes, right? 3 falls down in front, 15u squared, 15u squared. And then when you replace the u, it's 15x squared. So listen, obviously the power rule is a lot faster. I mean, duh. But I'm just trying to show you that you could actually use the chain rule in that scenario if you want. And this is what I was trying to really harp on earlier, is that any function really could be viewed as a composite function if you just let u equal x. I know it's kind of boring and unnecessary, but it works. All right, let's look at this problem. I'm actually going to show you, believe it or not, I'm going to show you 3 different ways to do this problem. You're probably going to hate me, but I'm going to show you 3 different ways. The first thing you could do is a lot of kids will look at this and say, oh, quotient rule, something divided by something else. So we could use the quotient rule. Okay, so to find the derivative using the quotient rule, it says to start with the bottom, 3x plus 1. Multiply by the derivative of the top. The derivative of a single constant 2 is 0. Minus, now we're going to take the top and multiply by the derivative of the bottom. The derivative of the bottom is just 3. Again, 1 falls down, 3 times 1 is 3. X to the 0 is 1, so 3. The derivative of 1 is 0. Okay, get it. All divided by the denominator squared, 3x plus 1 squared. All right, cleaning this up, we get, let's see here, 3x plus 1 times u, or times u, oh my gosh. 3x plus 1 times 0 is completely wiped out, so we get a negative 6 on top, all divided by 3x plus 1 squared. Very, 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 very easy, very, very fast. I mean, come on, so simple, right? All right, another way you could do this problem is, again, using a version of the chain rule, where you say, okay, I'm going to let my parent function be 2 over u, and I'm going to let u equal 3x plus 1. So I got my parent function, y equals 2 over u, and then I'm looking at the u as the denominator, 3x plus 1. All right, so to find the derivative, I have to first find the derivative of my function, and I'm going to actually think about this as 2u to the negative 1. That's going to make it very easy to use the power rule. Negative 1 falls down, I get negative 2, u raised to the negative 2. Negative 1 minus 1 is negative 2. But then again, remember the chain rule says then you have to multiply by the derivative of u. The derivative of u is just 3. There it is, right? The derivative of u is just 3. So now I got to clean this up. All right, negative 2 times 3 is negative 6. I'm going to replace u with what it is, 3x plus 1. to the negative 2. And then I'm going to say, whoa, 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 wait a minute. I don't like a negative exponent. The negative 6 stays on top. The 3x plus 1 moves to the denominator where it can become squared. Voila, the same answer that the quotient rule gave me. How easy is that? And I'm going to show you one more way that we could use the chain rule. Check this way out. The first thing I'm going to do is I'm going to rewrite the function. Watch how I'm going to do this. 2 times 3x plus 1 to the negative 1. You might be like, wait, what? Remember, this denominator could be viewed as one number all raised to the first. And anytime you want to move to the denominator, to the numerator, denominator, just make your power negative. So this would be equivalent to 2 times 3x plus 1 to the negative first. I know that that's kind of a weird way to do it, but it works. Then I could just go right into the chain rule. To find the derivative, negative 1 falls down in front, negative 2. Leave the inside alone, 3x plus 1. New power is negative 2. But then don't forget, a big part of the chain rule is saying that then you got to multiply by the derivative of the inside. The derivative of the inside is 3. So I get y prime equals negative 6 over 3x plus 1 squared. Negative 2 times 3 is the negative 6. And then again, I don't like negative exponents, so I move it to the bottom as 3x plus 1 squared. So 3 different ways that all result in the same answer. My point is, I don't care. If you like, hey, the quotient rule is really easy. I like the quotient rule. If I see something divided by something, I'm going to use the quotient rule. Awesome. But if you look at that as the chain rule, and you're going to say, I'm going to let u equal the denominator, 3x plus 1, use the chain rule. Or if you want to use the shortcut chain rule, like the fast chain rule, it's just saying, listen, I don't need to write a u. I can see how the negative 1 falls down. Leave the inside alone, 3x plus 1 to the negative 2. I just have to remember to multiply by the derivative of the inside. I mean, that's it. I know that the chain rule is a little bit confusing, and I'm making it very simple because, yes, I have learned it. I know it. But, take the time to process it, work on some examples. It's really not that bad of a rule as long as you see composite functions within. All right, guys, love you a lot. That's it for the derivative rules. Now it's time to put them to use and really get good at them.